Dear students, after studying this module, you shall be able to know that pure form of isomers can be obtained from a racemic mixture. Understand the process of resolution. Learn about the different methods of resolution and analyze the efficacy of various methods of resolution. In the previous modules, we have discussed in detail various types of isomers, that is enantiomers, diastereomers, erythro and thioisomers, etc. When an enantiomer is converted into a racemic mixture or a racemic modification, usually through a chemical reactions, this process is known as racemization. Conversely, when a racemic modification is separated into its constituent enantiomers, the process is known as resolution. In this module, we shall focus our attention to various methods of resolution and their efficacy. Preparation of a pure stereoisomeric forms or resolution is an indispensable part of many stereochemical investigations. Only after this is achieved, many further steps can be undertaken. The study of physical properties of stereoisomers and of their chemical reactions. Another route to the preparation of pure stereoisomers is furnished by stereospecific reactions, which involve the formation of the desired stereoisomer free from the impurities of the other forms. Methods of resolution. Most of the natural products, foodstuffs, drugs, flavoring agents, perfumes and other biologically active materials usually show their desirable or beneficial effects in one enantiomeric form only. That is, plus morphine is the powerful analgesic. On the other hand, its negative isomer is not. Thus, resolution is the method of considerable practical importance. Nearly all modern methods of resolution of racemates rely on the classical experiments carried out by Louis Pasteur about 150 years ago in 1848. The basic resolution methods are developed in and around the experiments carried out by Pasteur. Firstly, the mechanical separation, a method also known as spontaneous resolution. It depends on the crystallization of the two forms separately, which are then separated by hand. Chemical resolution based on the formation of diastereomers. Resolution by the biochemical methods, which makes use of the ability of microorganisms, their enzymatic systems, to destroy one enantiomer more rapidly than the other. Adsorption methods, in particular chromatographic techniques. A considerable improvement has been made in this area since then. In this module, we will discuss the various methods of resolution in depth. Efficiency of resolution. The efficiency of resolution method is estimated by optical purity of a pure product obtained and is expressed by P in percent, where P is equal to 100 as a multiplied with the ratio of the molar concentration of the product to the molar concentration of the pure enantiomer. Numerically, the optical purity corresponds to the excess of one enantiomer over the other in percent. It does not coincide with the fraction of an optical antipode in a mixture. The various methods of resolution and its details are discussed at length. Firstly, the resolution by mechanical separation of crystals. The first resolution ever to be brought about was achieved in this way as started earlier by Louis Pasteur in 1848. Pasteur prepared the sodium ammonium salt of racemic tartaric acid and allowed it to crystallize in large crystals by slow evaporation of aqueous solution. He then picked apart the two kinds of crystals, making use of the fact that they showed dissymmetry in the crystal state. The more useful variation of mechanical separation is the method of inoculation, originally discovered by Guérinez. If a saturated solution of a racemic mixture is carefully inoculated with the pure crystal of one of the enantiomers, the crystal will grow and an appreciable amount of an active isomer shall be separated from the racemic mixture. For example, plus sodium ammonium tartarate can be crystallized from a solution of racemic modification not only by inoculation with the crystal of plus salt but also by inoculation with minus asparagine. Crystallization methods by themselves are rarely practical methods of resolution, but they are often used in the practical way in conjunction with the other methods. For example, phenyl methyl carbonyl hydrogen phthalate. After being resolved to the extent of about 95% or so by means of brucine, is dissolved in carbon disulfide and seeded with small crystal of the racemic compound. In this particular case, the racemic compound is less soluble than enantiomers, and so most of the excess of it is left. The resolved phthalate crystallizes out. The mother liquor is decanted and problem ether added to it, whereupon the enantiomeric phthalate crystallizes in turn. In other cases where a racemic mixture is formed or where the racemic compound is more soluble than the enantiomers, the active forms may be purified by crystallization, any residual racemic material remaining in the mother liquor. Resolution by the formation of diastereomers. When a racemic modification is allowed to interact with an optically active material to give a derivative such as salt, in actual fact, two diastereomeric derivatives result. For example, in a reaction of racemic acid plus A with an active base minus B, the individual molecules of the acid are either plus or minus, and therefore the individual molecules of the salt formed are either plus A minus B or minus A minus B. These two types of the salt molecules are evidently no longer enantiomers but now diastereomers. Therefore, they have the properties different and maybe in general be separated on the basis of the difference of properties. Several conditions should be fulfilled by good resolving agent. First, the compound between the resolving agent and the substance to be resolved should be easily formed and should be easily broken up. For once one of the diastereomers, example minus A minus B, is obtained in the pure state, it must be decomposed chemically so that pure minus A may be recovered. This condition is generally met by salts, which are usually formed rapidly by mixing the organic acid base in a solvents and may be decomposed following resolution by treatment with the mineral acid, if the organic acid is to be recovered, or mineral base if the organic base is desired. Resolution through the formation of a molecular complex. Instead of forming stable salts or covalent compounds with the substrates and the resolving reagents, it is possible in few cases to have a molecular which forms easily and thus are ideally suited for resolution. The first observation was made by Pasteur in the formation of molecular compounds between amides of malic acid and of tartaric acid. Digitonin, as shown in the figure, which is steroidal saponin, forms addition complexes with various alcohols. Example, alpha terpineol, isocarbomenthol, and phenolic compounds which can be preferentially crystallized from appropriate solvents and then decomposed to give enantiomerically pure alcohols and phenols. List of the compounds with the resolution carried out with the complex formed are given here in the table. Resolution by chromatography. The chromatographic methods of resolution of racemic mixtures is carried out generally under 4 different conditions. Firstly, formation of diastereomeric mixture by derivatization with the optically active reagents and separation by classical chiral using achiral adsorbents based on the different adsorption coefficients of the diastereomers. Secondly, direct resolution of the racemic mixture using chiral of the adsorbent materials either as a solid or as a liquid stationary phase. Thirdly, direct resolution on the achiral solid phase using a mobile chiral liquid phase. And finally, the direct resolution using an achiral solid stationary phase modified by the chiral reagents. First method is an alternative to the separation by crystallization of diastereomeric salts. The method is of general use and may be illustrated the resolution of 2-butanol by forming esters with mandelic acid, followed by the chromatography on the Dowex 50WX2 to give both the diastereomeric esters. The second method, namely use of chiral stationary solid phase, is more interesting. The naturally occurring polysaccharides and their derivatives provide useful chiral stationary phase materials. One, namely microcrystalline triacetyl cellulose, also termed as MCTC, forms a versatile column on which a number of compounds, example racemic olefins, biphenyls, ketones, alcohols, esters, acids and salts have been resolved, as has also been carried out shown by Hesse and Hegel in 1976. The problem is its relative unavailability. An alternative method of preparation of chiral stationary phase is the adsorption of chemical binding of a resolving agent to a achiral stationary phase. Thus, minus TAPA, as shown in the figure, adsorbed or covalently including helicines. Chiral crown ethers bounded to silica or organic polymers have also been used by Cram and Cram in 1958. In the third variation, many cationic chelated metal complexes, example tris diamino metal complex, have been solved of chromatography on the column of cation exchange CFA-dex, dextran cross-linked with epichlorohydrin by elution with aqueous solution of plus tartrate. In the fourth variation, an ordinary adsorbent like silica gel is made stereoselective by special treatment with optically active substances, for example, plus tartaric acid and plus camphor sulfonic acids, which are later removed by elution with the solvent, leaving behind a memory. Gas chromatography has also been extensively used for analysis as well as separation of enantiomers, working on the above principles. The trifluoroacetyl derivatives of the optically active amino acids have been used for gas chromatographic resolution of racemic alcohols via the corresponding esters. Paper chromatography can also effect partial resolution. In the paper itself, cellulose material can act as chiral adsorbents, or it may be impregnated with the solution of optically active compounds such as camphor sulfonic acids. Resolution through equilibrium asymmetric transformation. The resolution technique based on the principle of equilibrium asymmetric transformation involves two steps. Firstly, epimerization of a diastereomeric species, be it a covalent compound, a salt or a complex in solution, and then the precipitation of the predominant epimer. If the asymmetric center undergoing the configurational change can be separated from the rest of the diastereomeric species, only one enantiomer is obtained. In ordinary resolution, the yield of enantiomer can never exceed 50%, but in asymmetric transformation, the racemic form can, in principle, be completely converted into one of the enantiomers. When the racemic form of 2 para-carboxybenzyl 1-hydrinanone is treated with bromine in acetone solution, one of the diastereomers precipitates in over 90% yield. On acidification, the plus enantiomer of the ketone is obtained, which however racemicizes spontaneously. The given structures show the equilibrium asymmetric transformations. Resolution through kinetic asymmetric transformation. The kinetic asymmetric transformation is based on the principle that one of the diastereomer is formed, destroyed or transformed selectively by chemical reaction. This is possible because the activation energy of the diastereomeric transition states in the reaction of a racemate with the chiral reagent are different, and so the two enantiomers react at a different rate. Resolution by biochemical transformations. In the kinetic method of resolution as discussed above, the chiral reagents may be replaced now by the microorganisms or the enzymes, which are often highly stereoselective in their reactions. Pasteur first observed that when a solution of ammonium salt of plus minus tartaric acid is fermented by yeast or a mold, which is Penicillium glaucum, the natural plus form is completely consumed, leaving behind the ammonium salt of minus tartaric acid. The biochemical method has found an important application in the resolution of plus minus or the racemic amino acids. The shortcomings of the biochemical transformations are as follows. Very dilute, usually aqueous solutions have to be used for fermentation, thus the product may be hard to isolate. The enantiomer, which is biologically more important, is often selectively consumed. It is very difficult to find an appropriate microorganism for a particular substrate. Resolution through inclusion compounds. Some compounds crystallize in such a way that a hole is formed inside the crystal, which can accommodate another guest molecule without forming any chemical bond. These complexes are known as clathrate or inclusion compounds. The inclusion of the guest molecule depends on the steric fit inside the crystal lattice and is often very selective. Desoxycholic acid, a stereoidal compound, forms such crystals in which a particular enantiomer of the selected molecule can be included. It can be used for the resolution of camphor. Methods based on NMR spectroscopy. NMR spectroscopy is extensively used for the determination of enantiomeric purity. Use of diastereomers. Since any two corresponding ligands or nuclei in two enantiomers are enantiotopic by external comparison, they are isochronous and cannot be distinguished by NMR working under achiral condition. But if the enantiomers can be first derivatized with the optically pure reagent, two such ligands will be diastereotopic by external comparison and surely will then have a different chemical shifts. Use of the shift reagents. Chiral shift reagents, as shown in figure, are also extensively used to determine the enantiomeric excess by NMR. They form diastereomeric complexes with the chiral substrates having a variety of functional groups and at the same time induce increased anisochrony into diastereotopic groups of protons. Use of chiral solvating agents. In yet another variation of NMR methods, a chiral solvating agent CSA is used which forms the diastereomeric solvates with the substrate through weak solvent-solute interactions. The CSA may be either a solvent or a co-solvent or even a solid auxiliary. The most common CSAs are 2,2,2-trifluoro-1-phenyl ethanol and the corresponding anthracyl derivatives. As shown here in figure, the diastereomeric associates with CSA through the hydrogen bonding. To summarize, in this module we have taught you that preparation of pure stereoisomeric forms or resolution is an indispensable part of many stereochemical investigations. Only after this is achieved, many further steps can be undertaken, the study of the physical properties of the stereoisomers and their chemical reactions. Nearly all modern methods of resolution of racemates rely on the classical experiments carried out by Louis Pasteur about 150 years ago in 1848. The basic resolution methods are developed in and around the experiments carried out by Pasteur. Mechanical separation, a method also known as spontaneous resolution, it depends on the crystallization of the two forms separately, which are then separated by hand. Chemical resolution based on the formation of diastereomers. Resolution by the biochemical method, which makes use of the ability of microorganisms, their enzymatic systems to destroy one enantiomer more rapidly than the other. Adsorption methods, in particular chromatographic techniques. The efficiency of a resolution method is estimated by the optical purity of a pure product obtained and is expressed as P in %.